So 6.2, I'm not going to do 6.3 straight away. I'm going to give you guys a break because it's quite a lot of notes here. Okay, a lot of definitions. So we all know that an ordered pair is a bracket with two numbers that just depict where something is, with the x's and y's. A relation is simply a whole group of them together. So if I have here, if I plot those points together, something is happening between the x's and the y's in regards to those four sets of coordinates. And we know that the relation is like a relationship. X is related to y in some sort of way. That relationship is defined by the equation y equals x plus 2. There's a connection. When you have a connection with your friends, okay, connection with your family, okay, and obviously we can draw a line that makes that relationship quite clear. Please interrupt. I don't mind interruptions today because it allows me to get my breath. Sketch a graph of each of the following relations and state its domain and range. Once again, you've got your ordered pairs with curly brackets as that group. Okay? And sometimes it can actually just be random. There may not actually be a relationship. It's still a relation, but it's not a relationship. You can't see much of a pattern there. But if I go out a bit more, the question was asking the domain and the range. Because we're jumping, you're jumping as in like hopscotch from one dot to the other. If you're jumping from dot to dot, we must use curly brackets and pinpoint each of the times an X appears. And we do that in order. With the range as well, you can see we have a range. It doesn't go from -2 to 3. It's at -2. It's at -2 and it's at 3 with the curly bracket. You're jumping. No in between. If you give me a range, normal bracket, and you do -2 and 3, it'll be wrong. Okay. We should all be okay with graphing when it's in 4x plus 2y mode. It's not in y equals mode. You should be comfortable with that already. But it states that we're looking at x's and y's such that our relationship, but we're only interested in x equals 0. What does that mean? I think I might film myself in front of the TV there. It might be better for you at home. All equations go all the way to infinity, all the way down, but we like to cut things off. So in here, if I'm all the way, this is x less than 0. So I have to cut that, like my sword is coming down, I have to restrict it so that its x is greater or equal to 0. Does that make sense? We're not interested in anything over here. We're only interested from this point on, where x equals to 0, and on the y to 4, and all the way down. On our domain, we're going from 0 to infinity, but on our range, our up and down, we're going from negative infinity, and this lift goes all the way up only to level 4. Okay, kind of like one of those Resident Evil bunkers that go further down into the ground, and it only goes to level 4 above the ground. Okay. Okay, same thing happens here. You don't need to really explain that one there. Once again, I'm interested from -2 to 3. These aren't curly brackets for the x values. So I'm only interested between -2, 0, 1, 2, and we stop at 3. This line goes on forever, but we have a window in between here. Okay. So on both ends, it's cut off. Sometimes one end is only cut off. Once again, domain and range. Domain was already in our question. If you ask the range, you need to work out where it stops. Starts at -8. Black dot to include it, all the way up to 7, which is right there. Okay. So in here, now we're starting to do it with quadratics. Please don't forget everything that you've done in the past. If we're going to graph this, we just simply graph it as normal. What are the features of our quadratics again? What are they? What do we need to find out when we're doing a graph? Feature. Y-intercepts are the most important. Good. What's the second most important thing? The x-intercept. So yeah, all intercepts. Good. And the turning point. What is the technique that we use to find out the turning point? We complete the square. What's the other one? If you don't like completing the square, you can do it another way. What is it?
-b on 2a.
-b on 2a, which is, what do we call that? It's the axis of symmetry. So we're finding out the halfway, as Gabe has said, this gets us the halfway, which gives us our turning point. Okay, once you find your x, you can then find your y. You substitute it in. I've just listed down one technique here, completing the square. If you complete the square with this, these two are the same thing. This is nicely showing us that we have a turning point at where? Where's our turning point?
2 and 5.
At 2 and 5. Okay, so that would be 2, and that would be 5. That one there. Okay, like so. Okay, looking at the domain, some of you have already seen it already. What are the x values for this cubic here? I just showed it, if you saw it. From one end, from the left to the right, where does it start and where does it finish? How far do I go left with this one, quadratic?
It does.
It doesn't stop. Okay, negative infinity. How far with this quadratic? So I go to the right.
Yeah, finishes.
Infinity. Okay, quadratics don't end on the left or the right, only if you want them to. However, for quadratics, their hills or valleys, how far down is this quadratic guy? How far down? This quadratic, I've got arrows there. But how far does it go down? In regards to y values, how deep does it go down into the ground?
Infinite, no?
Infinitely.
So,
Thank you, Zaid.
like,
This hill has no limits. It's going all the way down, like into hell. If you believe it, hell's down there. Okay, goes down into hell. But this valley, this quadratic doesn't go all the way up to heaven. What does it allow you to go to? To 5. You didn't make it to heaven, you made it to level 5 of the sky. Okay? Not quite good enough. Okay. So how to explain domain all the way from left to right is the infinities, left to right. For this one here, the range all the way down into hell, negative infinity, up to 5 only. Doesn't go all the way up. Our R simply means if you want to write less and not write that, just write R. That covers all x values. Any questions? Okay. We're going to sketch y equals x squared plus 1 for x element of -2, 3. So now's the chapter where you have to be paying attention to restrictions. You're not just graphing anymore and doing whatever you want. They are asking now for restrictions. You are going to graph that, but we're going to restrict it. Where x, what does this weird e stand for? Element of our x values from -2 to 3. So I'm only interested in going from -2 to 3. This is an x squared plus 1 graph. In your earlier chapters in this year, you would have gone all the way. But now we're restricting. From -2, got to stop there. I'm not interested in anything there. You stop. It's an open dot. Why is it an open dot? Because in the first sentence, what is it? It's a round bracket. Closed dot, square bracket. Okay? If I put in -2 in here, what's -2 squared? Plus 1. That's why it's 5. Likewise, I go here. 3 squared is plus 1, 10. 3 lands at 10. Our ends of the quadratic. Okay? Now, they're going to ask you about the domain. What is the domain? What's the domain? Can anyone work out the domain? It's in the question. -2 to 3.
Yeah.
Trick question. What's the range? Be careful here. What's the range? It's going from here up to somewhere here. What levels does it start here? And it rises up with the y values. It's 1 to 10. Tim, do you want to close your brackets or leave them open? From 1 to 10. At 1, close or open? You said 1? When you write it out, the range, what sort of bracket do you want to use? For 1? Who says open? Who says closed? It's closed. Closed is correct. Okay, closed is correct. It's closed at 1, and it's also closed at 10, because it's coloured in. You will lose marks if you put these in normal brackets. That's what I meant. Sorry, Tim. My question wasn't clear enough. Okay. From 1 to 10. Did you go through definitions of functions last year or what they mean specifically. Okay. All right. A function, so they're all relations. Everything's a relation. I'll have this in the notes. And these branch out into things we call functions and non-functions. Two main groups. We separate all the graphs on the left and all on the right. All on the left are functions, but what's a function? One y value for one each x value. 1 to 1, 1 for 1. We're not sharing values, 1 to 1. Okay, and how do we test for that? Let's look at this question here. Okay, oops. Which of the following sets of ordered pairs defines a function? Okay, this is a function that we've called S. -4, 0, -2, 3, -1, 5. Is that a function or is that not a function? It's lolly time. Keep you focused. Who wants to have a go? Amy, function or not a function? Why do you say it's not a function? Okay, functions, one value, no sharing involved at all.
Oh, it's function.
It's a function. Why?
Like the same numbers.
There's no same numbers anywhere. Okay? Okay? This is a function. They're not sharing. Okay? There's your lolly for the first lolly. Okay. If you drop your lollies, you have to throw them back. Okay. Okay. Gets a bit trickier. I've got 3 dots in here. Is this a function or is that not a function? Is there any sharing involved? 1 to 1. Okay. Who would like to have a go? Who wants to back themselves? Jesse's going to back himself. Function or not a function? You got a 50% chance to get this one right. No sharing of x's or y's. It's a function. Why Jesse? There's no sharing of x's and y's. Okay. I didn't actually write that there, but you can see there's no sharing. Okay. Okay. Jesse, great. Okay. Actually, I made a mistake. This is the same question. Okay. It's still right. I just plotted it visually. I gave that lolly away for nothing. So I'm down a lolly for the 10. Okay, we've got another function. Pairs up. Not a function. Why? Sharing, what are they sharing? Which coordinate? There's 2 3s and 2 4s. A lot of sharing all over the place. Okay? Sharing, we don't want to share in functions. Okay? No sharing allowed. I know that sounds bad. S is not a function. As Chris said, 2 y values or an x value specifically. So x is 3. X is 3, but at 3, it's also 2, and it's also 4. Okay, so this is what's happening. I've plotted those points in there. If you're a visual person, to find out if a function is not a function, what test do we give it? Okay, we give it. Notice that 3, it's also 2 and 4. So we use the vertical line test. You can use your ruler on a graph. If you line it up anywhere, and if it hits twice, it's not a function. Here it's still a function, but over here, it's not. because this vertical line tells us for one x value, it hits at 2 and 4. Vertical line test. That's a proper test. That's the visual test. If you're more visual. Vertical line test, that when it is cut, when you cut a graph, its function when it cuts once. Okay, but if it hits twice, more than once, it's not a function. Vertical line. Don't get confused that with the horizontal line test, which is coming up. Here now, circle here. Nathan, the circle, function or not a function? Not a function. Not a function, Nathan. We like circles. Circles are nice and pretty, but they're not functions. It cuts twice. Okay. Here. Right. Amrita, it's quadratic. What is it? Function, not a function. It's a function. Why? There's no shared values. Also, why? What's happening with the vertical line test? Cuts once. Cuts once. Okay. Okay, we're moving on into f, x, y notation. Looking at A, are you guys exposed to that already? That's if y equals 2x plus 1. Are you familiar that f of x is y? Have you been exposed to that yet? Have you done questions? Okay, good feedback. Okay. All right. You're all good with y equals to x plus 1, but y is dependent on what x is, isn't it? Whatever y is the answer, it's dependent on x. In the same way, we can rewrite it as f of x or function of x. Y has a functional relationship with x, and that relationship is 2x plus 1. Y depends on 2x plus 1. It depends on it. It's a function of what happens to x. This is function notation. And we've been defining functions all the time right now. It's a function. That's how you write it, f of x. X and y, what does that mean? It means we're interested in all x's and all y values at the moment. Okay. R to R simply means this is what it means. This first R, what does R mean? Two lollies. Okay. States with higher. What does R mean?
Rational.
No. Real. What were you going to say, Amrita? Real. Okay. I'll give 1 to Tim. Oh, was it? 10. Sorry. And Amrita? Try again. Keep everyone awake during this lesson. Real simply means we're interested in everything at the moment. This is what we got. Real. All the way from left to right. And this thing is going to map onto our graph that has real numbers in there. That's all it is. If you do specialist, you might do R2 or even R3. But I'm not teaching specialist. And I've never taught specialist. I did it in high school though. Can someone explain to me in English or the language that you speak normally in your head first? Like my dad Filipino. When he thinks in Filipino in his head. Mind-boggling, isn't it? It's not English. His first language is Tagalog, Filipino. What does that mean to you? Can someone explain? How do you make this clear to you? What words would you use? What are you instructing yourself to do? Who wants to have a go? Got 2 lollies. There's really 2 things you need to say here. 2 main things. And Rita, what's the first thing you're going to do? Y is related to X with what? Yeah, keep going. You're on one lolly so far. 3x minus 2, okay. And then what would you say after that?
Where X is greater.
What does that mean?
Zero the values that is where X.
Okay, Perry has said, and then Rita, we have an equation that we're going to grab, and we're only interested in x values that are greater or equal to 0. Okay, do I owe you a lolly, Perry? Okay.
And it's fine.
Okay.
And you say to the unit function.
We're going to draw a line with a boundary all the time. Any graph that you do, you've got the graph and a boundary from now on. Graph and a boundary. Graph and a boundary. Another way you can rewrite this, as we said, instead of y, we can use the notation function of x. Okay. Now notice that this first part, in any of your functions, the very first part is always the domain. Okay? In here, our domain is x is greater or equal to 0. That's our domain. If you want to rewrite it, if you're asked to rewrite it in function notation, this is our original R, but we're only interested x is greater or equal to 0. How do we write that? We're only interested in all positive real values with 0. That's our domain. Domain is the first section before your arrows, every single time. Once again, an equation, domain. -2, x 5. Our function is 2x squared plus 4. But the first section, when we write our function notation, is the domain. We're going from -2 to 5. We write it with our brackets. We're just rewriting everything in function notation. Okay. Does anyone know what type of what graph this is called?
Exponential.
It's not an exponential. You're close though. It starts with a T.
Truncus.
It's a truncus, see? Very good, see?
The other one.
You don't want to? Okay.
I'll take it.
Zaid, would you like to give this lolly to anyone?
You can give it to whoever else for him.
Okay. Who was first? I think Rita. A lot of sugar at the start of term 2. Now, we've got a domain here. X can't equal 3. Y. Hudson. Why can't x equal 3? Why is our domain saying x can't equal 3? Why? No idea. Who wants to have a go?
Because the dominant angle equals 0.
Thank you, Tim. If x ever equals a 3, let's do that. 3 take away 3 is 0 squared. And Tim said 0. You can't have a 0 on the bottom. It's undefined. Okay, that's the giveaway of our domain. You can be everything else except for 3. How do we write that? We rewrite the y with an fx, but the way to write domain is everything except the number 3. The number 3 is cast out, set aside. We don't want number 3. We want everything else there. Okay, and it's a backward slash, not a forward slash. It goes like that. It doesn't go like that. Okay. Have you guys done this before? If you've got your function in here, if the x turns into a 2, you're simply substituting all the x's with 2's to get the answer. Okay, who knew that before? Hands up. Okay, hands down. Same with -1. Be careful. -1 squared becomes a positive when you do your calculation. Sometimes you can substitute an equation within the equation. It's messing with your head right now. So in every spot where there was an x, you are putting an x plus 2 instead. You're substituting an equation into the other equation. Our equation is x plus 2. That was my x, that was my x. They're all changing to x plus 2. And then you do your expanding workout from chapter 1 and 2 from this year. Sometimes you can substitute other letters as well. In this case, it's 1 over a. And you better get used to that as well. This sort of thing, especially in year 12, they love doing this to you guys. Substituting 1 on a different letter, expanding it out, and so on. Okay. Having a look at this, consider the function defined by fx equals 2x plus 1 for all of x, element of R. Find ft. How would you find ft? What would you do? ft. What was the one thing there's only one thing that needs to be done here, Gabe. What is it?
Substitute t for x.
Done. Correct. ft is no longer fx. X has changed to t. We change that x into a t. Almost there for our first break. Okay, we're going a bit further now. It now says find the value of t for which ft equals 7. We've changed x to t. There's another instruction here. They haven't said it. They're implying. You have to read between the lines. Thank you, Tim. This ft is this ft here. Tim is saying, let's replace it because it's equal. This now becomes 7.
I'm right.
Okay. Our ft became 7. And then you do your backtracking to get t by itself to equal 2. Okay. What would you do in this case? ft equals t.
Same thing.
Same thing. Instead of a 7 this time, the t is now the 7. I've just rewritten it the other way. Okay. Backtracking.
That's classic.
Okay. This one here, for what values of x is f of x greater than equal to 2x? What are we going to do? We start off with the first line. But what's our f of x going to, what are we going to change that to? Instead of 3t plus 1, what's our original equation? 3x plus 1. You change it to 3x plus 1. Then you do your algebra working out to get x by itself. And x is going to be greater or equal to 1 or negative 1. Okay, let's see. Let's see how far we've gone into the notes. I just want to gauge because I've been talking a lot. There's a heap here. Do you guys want a break? Okay. You guys have a 2-minute break. We're back here in a second. So we're now going to tackle questions on the whiteboard so you know what's required. A lot of gibberish happening here. Tim, Hudson. Sketch the graph of the function where f such that negative 3 to 2 goes to real numbers, function of x equals x plus 2, and then state the range. We want to sketch and then state the range. But I haven't talked about domain. But what's the domain? Okay.
Negative 3 to 2.
Negative 3 to 2. It's staring right at you. They don't say that the domain is negative 3 to 2. They just write it in the spot where you should be translating it as the domain. Negative 3 to 2. We all know how to sketch f of x equals x plus 2. Okay, what sort of graph is that? It's a linear. It's a line. It's simply, in plain language, y equals x plus 2. But what would be some good values to try and plot first? Okay. Okay.
Your y.
Y-intercept? Yes, good. In that case, what changes to 0? The x or the function of x? The x. Okay, yep. The x. Okay, yep. Sorry, I was confusing my own head. Okay, so y-intercept. Okay, function of x. Is this an x or y value? The two. X or y. So when x equals 0, y equals 2. Or x function of x. Or to what you're used to, x and y. Function of x is a y now. You need to get used to that. Okay, so we've got 0 to 2, which is about here. We make it. Yeah. We've got 2. What else would you plot in this graph? What's the minimum amount of dots that you need to draw a line? 2. What's another one that we can use?
X-intercept.
X-intercept. Okay, so Emily's going for X-intercept. At X-intercept, what are we doing?
You're making f(x) equal 0.
Good. So in the olden days of term 1, y equals 0. But now we are in a new phase. We are in a new era. Function of x equals 0. So what we do here, in our equation, this is now 0. And from backtracking, x equals -2. So we can plug -2, 0, -1, -2. Okay, so we've got our line. But what are we going to do to this line? What do we need to do to this line? Okay.
Apply the domain.
Apply the domain. Okay. So we are only interested going from -3 to 2. So it's in our best interest to see what's happening at x equals -3. It's also in our best interest to see what's happening at f equals 2. And we can know what's happening. Our x becomes -3 plus 2, which is -1. Over here, we're simply changing
Good.
2 plus 2 equals 4. It's a substitution. So we have the coordinates of -3 and -1, and 2 and 4. So 2 goes up to 4, which is there. And -3, -1 is down here. Okay. Do I want to color my ends or open them up? We're only interested from there. We'll leave them colored in for the reason that they're included with square brackets. You're practically doing the same thing, just with different symbols now. Here, we didn't answer the question of the range, but we know this is at -1, this is at 4. Start, finish. Square brackets. Any other questions? We'll move on. Now, this is where it gets a bit tricky. Okay. In the universe, in graphs, relations are everywhere. It's in everything. As I said, we have functions on one side and non-functions on the other side. As we define them, we started off with a vertical line test, which said only one y value for each x value. More than, or not a function, is one x value, but two y values start appearing. That's not a function. Okay. Now, this is, just keep that in mind. I've got these on the notes. What happens now is for functions only, there are two categories functions are now can either be one-to-one or many-to-one. What does that mean? This is what this means. If I have one x value for each one y value, that means if I do a cut like this, what test would you call this? You call this a horizontal line test because it's horizontal. Okay. If it cuts once, what's that saying? There's only one x value for one y value. But if our graph starts getting cut up a few more times more than once, what does that mean? It means that there are two x values or more for one y value. Notice this could be 3 on the y-axis. That could be 3. But there are 3 x values that are sharing that 3. Okay. It's really easy to get this confused with the vertical line test. So let's do a couple of examples before we take a break. All right, which of the following are one-to-one? I've got 1, 3, 2, 6, 3, 8, 4, 10. Now, it's saying which ones are one-to-one or many-to-one. This question implies that we are dealing with functions. We're not dealing with non-functions. What does that mean? If I plot these coordinates up and I cut them horizontal line test at each of those points, there's only one cut or one dot involved. Okay, it's a function. If I move on to this question here, though, notice that I've got many x values for the one y value. What does that look like in a graph? It means that at 6, it's getting cut at 3 and 5. 3 and 5. Being cut twice for the horizontal line test. Okay. So we classify that as not one-to-one. Obviously, it's many-to-one. Okay. This one here. So now quadratics. Quadratics are functions. Jesse? It's not, they're functions, but it's a many-to-one function. It's not a one-to-one function. It's still a function though. Over here, the equation y equals 2. It's not one-to-one. Because that x y equals 2 is an infinite amount of x values that end up being at 2. It's not one-to-one, it's many-to-one. Sorry, there's a lot of me speaking today. But if you look at cubics, some cubics anyway, it is a one-to-one. No matter where I put this horizontal line, it only cuts once, which says for every x value, there's only one y value. Can anyone draw me a cubic on here where it's a many-to-one function? Who would like to go? Who wants to? I'll pause the camera because I'm not allowed to film you. For one lolly, who would it for 1? Who would it for 2? I'm at an auction now. Who wants 3? 3. For 4? even if you get it wrong. If you do it for five,
Jesse, did you say you were?
by the way, I actually got married on the holiday.
Oh, did you actually?
You can see I got a ring. Okay, so
Congrats.
if anyone comes up, I'll be more than happy to share some of my wedding photos. Who wants? You can see if I do a horizontal line test at 0, it cuts at a negative number at close to 0. Once again, at a positive number. Okay, it is a many to one function. Horizontal line test. Okay. Okay. Last couple of questions before I show my wedding photos. Okay. Y equals x plus 1 goes from left to right. Implied domains is what we mean by implied domain, Hudson. Implied domain simply means what's the domain. Sometimes it's not just R. In here, if our line goes from left to right forever, the implied domain, that is, when you say you're implying something without saying it, in the same way, we are saying, without saying, that our domain is R. There's no restrictions. Okay? Here, there is an implied domain here. Someone knows what this graph was before.
Exponential.
It's not exponential. Actually, it wasn't. I thought you said something else, Emily. I made you wrong twice. What is it? It's not a truncus. Starts with H. Hyperbola. Very good, Perry. Oh, I read that. Sorry. I read it. It's a hyperbola. Now, with this what do hyperbolas look like? If you were to describe a hyperbola, yeah, Zach's doing it. They're really weird. They look like an X. Okay. Now, we have here an implied domain. What is the implied domain without saying the domain? What is the domain without saying it? X can't be 3 is correct. Thank you, Amy. As you can see, X can't be 3 because 3 creates a 0 and we don't like zeros. So this is 0, but 3 here, there is an asymptote. Can't be, we've got to skip 3. We want R, we skip 3. Also, look carefully. Let's do it properly here. We'll do a bit of practice later on. This is 3. Oops. With hyperbolas, there's a skip where the denominator is. In this case, it's x minus 3, so x can't equal 3. But is there any y-intercept? Okay. There is no y-intercept. This 0 here gets skipped. It jumps from here to here. And you can't mathematically do it. Because if I want to find the x-intercepts, what do I substitute for x-intercepts? What becomes 0, the y or the x? The y. And if you were to multiply this denominator up, guess what happens to it? It all equals 0. It just falls over. It's like a black hole. Everything collapses. Can't have it. You can't have it. Okay. Okay. Square roots. Now, without graphing, let's ignore the square root for the moment. Let's ignore it. X squared minus 4x plus 3. What's that graph? What's the graph in the square root? It's quadratic. Okay. Our quadratic, we factorize as normal. X minus 1, x minus 3 is that trinomial factorization, okay? We're good with that. However, I now graph it. I'm not graphing the square root, I'm graphing the quadratic only. Okay, this is just the quadratic. Shh, boys, this is important. Jesse, keep your ruler to yourself. What don't we like about square roots? Not everything. What can't happen with square roots? Square root of a negative. What does that mean? So although we have a quadratic, we are not interested when it dives into the negative area between 1 and 3. Okay? That's the implied domain. So to avoid square root of a negative, which does not exist, we must have that x is greater or equal to 3, which is above, or x is less than or equal to 1, which is there. We are not interested in this negative bit. That's implied domain. These two are the same things. We marry the left and the right. They jump over the negative. Also, our range is all the positives with 0. Okay? So our range is positives there and above. Okay? Because you can't have the square root of a negative. We're only interested from 0. You can have a square root of 0 and positive numbers. Okay. When you are focusing for implied, when a question comes up, Zach, of implied domain, there are two things to look out for. Where square roots can't be negative, Hudson, and where denominators can't be 0. They're the two things to watch out for when they're after implied domains. Okay. This question here is just getting you used to, instead of F, you can use A. In here, area of a circle of a radius. So A area is a function of R. It's not fx anymore. But it's like fx. Instead of fx, we have AR. Okay. State the practical domain of the function A and find a 5. How do we do that? Might do this one on the board. Okay, lastly, 2 more questions. Sorry guys, there's a lot here. We'll just finish this off. I'll get another break. I know your head's bursting. We're talking about measurement here, radius. What's the implied domain? Practical domain. What's the implied? What are we interested in? Where can we go with this equation? And how far? Okay.
We can't cover any
0. Okay, can't have negative area, so we're going to start at 0. Can't have negative area. You can have 0 area, just not there. And how how far can we take this? This circle. How big can this circle be? Infinitely. We can go to infinite. Okay. Then it says find A5. That's easy. R becomes 5. So whenever I see an R, that's all it's asked you to do. It's substitute the radius for 5. Okay. I may stop there. Let's stop there. Okay, you've earned your second break.